I'm going to do a couple of examples of evaluating limits using L'Hopital's rule. Here's my first example. Limit is x approaches infinity of 1 plus 1 over x raised to the x power. If I think about the form of this limit, as x is approaching infinity, then 1 over x is going to be approaching 0. So this whole inside of the parentheses is going to be approaching 1. And as x is approaching infinity, then x is approaching infinity. So this is has the form of 1 raised to the infinity power. And so this is an example that we've seen a couple of times where I want to set this limit equal to y, and then I want to adjust this and put it into a form where I can use L'Hopital's rule. And the way to do that is to take the natural log of both sides of the limit. Natural log of 1 plus 1 over x raised to the x power. And then we know from properties of logarithms that if I have a log of something raised to a power, then the power can move into the front. And so that would be the limit as x approaches infinity of x times the natural log of 1 plus 1 over x. And now if I consider the form, as x is approaching infinity, I get x approaching infinity, and now this is the natural log of 1, which is 0. So I have a form now of infinity times 0, which is closer to letting me use L'Hopital's rule. And if I make one more algebraic change, and that is to let the limit as x approaches infinity of the natural log of 1 plus 1 over x, and divide that by 1 over x. Now the top is approaching 0 because it's the natural log of 1, and then the bottom, as x approaches infinity, 1 over x is approaching 0, and so I now have a form where I can use L'Hopital's rule. So at this point, everything that I've done up to this point is just getting the limit into a form where I can use L'Hopital's rule. One other thing that I'm going to do, because I've done it before and I know that it's easier, is that argument there, 1 plus 1 over x, that could be written as x over x plus 1 over x, which makes it the same thing as x plus 1 divided by x. It's going to be a little bit easier when I do L'Hopital's rule if I think about the ln of x plus 1 divided by x. And one other thing that I'd like to point out is that I am going to take the derivative of the natural log of x plus 1 divided by x. And when I do that, the chain rule says that I take the derivative of the outside, which is 1 divided by the inside, multiplied by the derivative of the inside, x plus 1 divided by x. And so what I want you to recognize, because I'm about to do it, is that this is 1 divided by a fraction, which allows me to invert the denominator and multiply. This is going to be the same thing as x divided by x plus 1 times the derivative of x plus 1 divided by x. Okay, so back to my limit. I have the correct form, so I can use L'Hopital's rule. So this is the limit as x approaches infinity of the derivative of the natural log of 1 plus 1 over x. So the derivative of the outside, leave the inside alone. That's right here. X divided by x plus 1. Then I need the derivative of x plus 1 divided by x. All right, that is the bottom, which is x, multiplied by the derivative of the top, which is 1, minus the top, which is x plus 1, times the derivative of the bottom, which is 1, all divided by the bottom squared. Then all of that gets divided by the derivative of 1 divided by x, which is x to the negative 1. That is negative 1 divided by x squared. All right, well, that's a bit of a mess, so let's see if we can clean that up. Right here, I have x minus 1. So this whole thing is equal to negative 1. This x is going to cancel with one of these x's. This negative 1 is going to cancel with this negative 1. So that might be a good place to stop. And it looks like I have 1 divided by x plus 1, one of those x's, all divided by 1 over x squared. Okay, again, a little bit more algebra. Limit as x approaches infinity of 1 over x plus 1 times x. If I'm dividing by a fraction, I can invert and multiply. Let me write that better. I can invert and multiply, so this would be x squared divided by 1, and that x is going to cancel with one of those, and that gets me the limit as x approaches infinity of x divided by x plus 1. All right, and so we've seen something like this before. Notice that this does have the form of L'Hopital's rule. This is now going infinity over infinity. So if I wanted to use L'Hopital's rule, it's pretty straightforward. X approaches infinity. The derivative of the top is 1. The derivative of the bottom is 1. This limit is approaching 1. Okay, so remember, this is not the limit that we were looking for. What I did was I just found the ln of y, and what I was really looking for was y. So what I have concluded is that the ln of y is equal to 1, which means that y is equal to e to the 1. So my grand conclusion is that the limit, as x is approaching infinity, of 1 plus 1 over x raised to the x is equal to e. Next example that I would like to look at is the limit as x approaches infinity of x divided by x plus 2 all raised to the x power. And what I'd like to suggest is that you pause the video right now and see how far you can get on this before you watch me do it. So if I check the form, as x is approaching infinity, I have x divided by x plus 2. That's going to end up approaching 1, and x is approaching infinity, so I have the form of 1 raised to the infinity. That's the same form as the last problem. So I will set the limit equal to y, and then I'll take the natural log of both sides. So natural log of y is going to be the limit as x approaches infinity of the natural log of x divided by x plus 2 raised to the x power. Properties of logarithms says that I can move the power down, so this becomes the limit as x approaches infinity of x times the natural log of x divided by x plus 2. Now if I check the form of the limit, I have that x is approaching infinity, and the natural log of x over x plus 2 is approaching the natural log of 1, which means I have infinity times 0. Again, that puts me closer to being able to use L'Hopital's rule. Then I get x raised to, or as x approaches infinity, if I rewrite this as the natural log of x divided by x plus 2 all over 1 over x, then I now have that the form is going to approach 0 divided by 0. So I am ready to use L'Hopital's rule. I've said this before. Up to this point, all I've done is change the way that the limit looks so that I can use L'Hopital's rule. Now I say I'm using L'Hopital's rule, and so I get that the limit as x approaches infinity, the derivative of the top, natural log of x over x plus 2 is 1 over the argument, which means I can flip that over, x plus 2 divided by x, multiplied by the derivative of the bottom, x plus 2 times the derivative of the top, which is 1, minus the top, which is x, times the derivative of the bottom, which is 1, all divided by the bottom squared. All of that gets divided by the derivative of the bottom, which is negative 1 over x squared. Got a bunch of stuff to clean up. In the top up here, I have x plus 2 minus x, so all of this is equal to 2. And I have an x plus 2 here, and I have two x plus 2's there. So let's see what I've got. Limit as x approaches infinity of 2 divided by x times x plus 2, all divided by negative 1 over x squared. I could rewrite that as the limit as x approaches infinity of 2 over x times x plus 2 multiplied by x squared over 1, and that negative right there, I'll put the negative here. This x is going to cancel with one of those x's, so I have the limit as x approaches infinity of negative 2x divided by x plus 2. Again, in the last example, I used L'Hopital's rule, but we have seen many times before that if the degree of the top is the same as the degree of the bottom, and we're taking a limit as x approaches infinity, then it will go to the ratio of the coefficients. So this is negative 2. Again, I did not answer the limit, I answered the natural log of the limit. So we just found that the natural log of y is equal to 2, which means that y is equal to e to the negative 2. So my grand conclusion is that the limit as x approaches infinity of, what was it? It was x over x plus 2 raised to the x is equal to e to the negative 2.